end of the year.
And good morning, everybody. Welcome back to Abstract Algebra. Thank you. Plan for today is we're going to get to it today. We're going to get to the fundamental theorem of cyclic groups that tells you if you have a cyclic group, here is exactly what all of its subgroups are. We're probably not going to finish our proof of the fundamental theorem until class on Monday, because we still have another couple of, we still have two more intermediate theorems today before we get to the fundamental theorem. So today, the plan is to do those two intermediate theorems, talk about the fundamental theorem, maybe like look at an example or two of it, and then Monday will be our day where we actually go through and finish proving the fundamental theorem. Speaking of which, Monday, I got my usual office hours, the hour before class and from 2 to 3. And as far as homework goes, homework 3 is due tonight. I know. And homework 4 has been posted on Blackboard. It will be due next Friday. So homework 4 is going to be due next Friday. If it makes you feel better, you will not have a homework 5 due the following week.
Is it because we have tests?
Yes. That's because you've got a take-home exam that week to do instead.
I saw that one coming. You couldn't fool me.
I was going to say, some of you know me too well, yes. I will tell you a little bit about the exam now, and here's something that might make you feel a little bit better about the exam. The exam's going to be like a homework, sort of, except it's going to have like from a bunch of different topics, and you're going to try and have a little bit of everything we've done so far. And for the exam, I will allow you one partner to work on the take-home exam with. Which means, and I'll talk more about this next week, which means you will be able to talk to the person about questions, like work on them together, but you will be responsible for writing up each of your solutions on your own. You're allowed to kind of talk with ideas about them, work with them, but you're not allowed to just copy each other's proofs, for instance. But, I don't know, it's helpful to have someone to bounce ideas off of, and other than, just me. And so, thought I'd extend that to all.
Do you want us to put our partners' names on our paper or anything?
Yeah, you will. I'll have a cover page for the exam that you'll have to submit with it, where that has a spot for your name and your partner's name. And woe be unto you if your partner puts down your name, but you do not put down your partner's name.
Oh.
I'll talk more about this like a week from now, after I've thought more about the exam. But that's kind of my plan. And just as a reminder, this will be the first of 2 midterms and a final. And all three exams, the 2 midterms and the final, will all be very similar in structure, and that they'll all be kind of focused on. They'll all be sort of like this take-home exam that you have a week to work on, and it's sort of like a homework set, except you're only allowed to talk to one other person, 2 other people if I am one of them. Wayne, Lauren, I'm glad you're so enthused about your punch. Any questions or comments before we get started today? Why are calendars always so nervous?
That's such a good segue.
Calendar.
Planner and calendar.
Oh, yeah, that was totally intentional. Calendars are always nervous because they know their days are numbered.
Right.
Alternatively, they're nervous because they have a date. So one of my 105s this morning guessed as the answer, and I liked it. Although it's too positive. I like my... Okay, so when we left off last class, we had just finished proving that if G is a group, A is an element of G, and A has finite order n, meaning n is the smallest power to which a to the n is equal to the identity. Then we said that for any integer k, the group generated by a to the k is always going to be the same as the group generated by a to the GCD of n and k. And we also said that the order, voice crack there, the order of a to the k is always just going to be the order of a, so n, divided by the GCD of n and k. And today, I wanted to start off by looking at a couple of corollaries to this theorem. This was a theorem. So I want to start off looking at a corollary, which is just going to say, in a finite cyclic group G, the order of any element little g in big G must divide the order of the big group. So in other words, I claim that in a finite cyclic group, if their cyclic group had order 10, for instance, then every element in that group has to have order dividing 10. So 1, 2, 5, or 10. So once we have this theorem, proof of this is pretty quick. We can just say that if G is generated by A, then any G in G must equal A to the K for some K. Hence, the order of G is just going to be equal to the order of A to the K, which, according to part 2 of this theorem, is just going to be, actually, let's say the order of A is n. So the order of G is equal to n, so we have a group of order n, finite cyclic group. Then the order of A in this case, or G in this case, which is by definition the order of A to the K, is just going to be n divided by the GCD of n and k. Hence, the order of G divides n, which is the order of the group at large. So in other words, if you're in a finite cyclic group, the order of any single element in the group has to divide the order of the big group. Any questions about this quick little corollary before we look at a couple examples? And you look very distressed.
I got it now. I just have to read it again.
Cool. Let's do a couple examples. So in Z mod 8Z, so that's the integer 0, 1, 2, 3, 4, 5, 6, 7. The cyclic group of order 8 under addition, mod 8. What can we say about the elements of, or the orders of any element in this group, according to this corollary? What are the possible orders that an element can have? So if we have a group of order 8, and the order of any element has to divide the order of the group, so 8. Peter?
1, 2, 4, and 8.
Bingo. Every element has order 1, 2, 4, or 8, according to this corollary. It's impossible to have an element of order 3. You can't have any element A such that A cubed is the identity, and that's the smallest power that'll take A there, because 3 is not a divisor of 8. Well, in Z mod 7Z. What can be the order of any element in the group? Okay.
1.
That's the only possibility?
No.
What else is a possibility?
7.
1 or 7. I was going to say, because that's going to tell us a lot about every element in the group, by the way. What element is going to have order 1? I'll give you a hint. There's only a single one in every group. The identity. So 0 is the identity in this group, which is going to be the only element of order 1. Because if A to the first power is the identity, then A has to be the identity element. And if you have an element of order 7 in a group of order 7, what do you know about an element whose order is the same as the order of the overall group? If you have an element that has the same order as the overall group, what does that tell you about that element's relation to the group?
It's a generator.
It's going to be a generator. So it turns out Z mod 7Z, and this will be true of Z mod PZ for any prime in general, every element is going to generate the entire group except for the identity element, which, if you're looking at Z mod NZ, the identity element's always 0. Any questions or comments? So, according to this corollary, in every cyclic group, the order of any element has to divide the order of the group. You think that's going to hold true in general? That in any finite group, regardless of if it's cyclic, the order of any element is going to divide the order of the group? Anybody like to make a guess? That I could cut to shreds with a single counterexample. No guesses?
No.
You're guessing that it's false? That this property has to hold true in an arbitrary finite group?
Yes.
Yes.
Are you just being contrarian to him, or?
Yeah.
Okay. Well, Peter, you're right. It actually does hold true in every group.
Oh!
I could cut it to shreds with a single counterexample, but there are no counterexamples to be had. Turns out this property is going to hold true in every group, but that's harder to prove. We're actually going to see that in a couple weeks when we prove something called Lagrange's theorem. That'll tell us this.
Even infinite groups, or?
Well, in infinite groups, its statement doesn't make sense. It would be, the order of any element has to divide infinity. What does it mean to divide infinity? Technically, yes, it holds true in infinite groups, and then you get into questions of what does it mean for one size of infinity to divide another size of infinity, and it kind of stops making intuitive sense at all. But yes, it technically holds true in infinite groups. Yeah, it does technically holds true in infinite groups. I convinced myself. Any questions or comments about what this corollary says? In that case, let's do another. And this will be our last one before we get to the big theorem itself. Because our next corollary is going to tell us that if A has order n for some A in group G, then it must be the case that A to the I power is equal, will generate the same group as A to the J power if and only if the GCD of I and n is equal to the GCD of J and n. And the order of A to the I is going to be equal to the order of A to the J if and only if the GCD of I and n is equal to the GCD of J and n. So we can say a lot about the relationship between two elements, that either they have the same order or that they generate the same group if and only if, as powers of A, if and only if the GCD of their powers and the order of A are equal to each other. So this one takes a little bit of work, but not too much. So here's our proof. Part one. We're going to suppose that A is an element of order n for some A in a group. So what we're going to do is we want to prove that a to the I and a to the j will generate the same set of elements if and only if I and j have the same GCD when taken with n. Well, we can actually say something slightly different using part 1 of this previous theorem. We can say that since the group generated by a to the I is equal to the group generated by a to the GCD of I and n, and the group generated by a to the j is going to be equal to the group generated by a to the GCD of j and n. So both of those are just coming from part 1 of the theorem we just proved. Order that the group generated by a to any power is equal to the group generated by a to the GCD of that power and the order of a, which is n. So since a to the I is equal to this thing and a to the j is equal to that thing, we need only show that a to the GCD of I and n is equal to a to the GCD of j and n, that they generate the same group if and only if the GCD of I and n is equal to the GCD of j and n. So in other words, we wanted to show that a to the I and a to the j generate the same group if the GCDs are the same. Using part 1 of this theorem, we can instead just prove that a to the GCD of I and n and a to the GCD of j and n will generate the same group if their GCDs are the same. That makes sense? Just kind of replacing one with the other using part 1 of the theorem from last class. So, first of all, we need to prove two things. Since this is an if and only if, we need to show if the groups are the same, then the GCDs are the same. We also need to show that if the GCDs are the same, then these groups that are getting generated are also equal to each other. Rowan, which direction do you want to prove first? Forward or backwards direction?
Forward.
Forward direction. Okay, Rowan wants to prove the hard one first. We can do that. So if a to the GCD of I and n generates the same group as a to the GCD of j and n, well, that means that the order of a to the GCD of I and n has to be equal to the order of a to the GCD of j and n. Why is that? Well, that's because we said the order of any cyclic group is equal to the order of its generator, so that the order of this group has to be equal to just the order of the individual element that generates it. And the order of this group has to be equal to the order of the individual element that generates it. So if these two groups, cyclic groups, are the same, their generators have to have the same order. Well, if the order of these two things is the same, we can use part 2 of the theorem from last class to say exactly what this is. The order of a to the GCD of I and n is, by definition, n divided by the GCD of n and the GCD of I and n. What? A GCD inside of a GCD. Which is just going to be the same as n divided by the GCD of I and n. So this is from part 2 of the theorem from last class. This right here. And similarly, a to the GCD of j and n, the order of that element, is, according to the theorem, n divided by the GCD of n and the GCD of j and n, which in turn will just be n divided by the GCD of j and n. Let me know if you want me to stop and go over anything here. And so, that tells us that n divided by the GCD of I and n is going to be equal to bip, boop, bop, blip, blang, n over the GCD of j and n. And then, I don't know, cross multiply, divide both sides by n, do whatever. That tells you the GCD of I and n has to be equal to the GCD of j and n. So in other words, if a to the GCD of I and n and a to the GCD of j and n generate the same group, that tells us these two GCDs have to be equal to each other from following this string of equalities around. So there's one more thing we need to show in order to prove this theorem. We prove that if the groups are the same, then the GCDs have to be the same. What else do we still need to show? Considering we were asked to prove an if and only if statement.
We have to go in the other direction.
Yeah, we have to prove the opposite direction, that if the GCDs are the same, then the groups are the same. But that one's pretty easy, because if the GCDs are the same, then you're taking the same power of A in both cases, and so the groups are the same. So then we can say if GCD of I and n is equal to GCD of j and n, here we're doing the backwards direction. Then clearly, then a to the GCD of I and n will be equal to a to the GCD of j and n. And if these two elements are the same, then they're going to generate the same group. Boom. Sometimes these arrows are kind of used to say when you're proving two different directions in an if and only if proof. I'm going to be using these arrows from now on, but when we say this arrow, an arrow pointing to the right, that means we're about to prove first thing implies second thing. And if we have an arrow pointing to the left like this, that's typically going to mean we're proving that second thing implies first thing as part of an if and only if statement. Questions or comments? Yeah, Peter?
Why is the GCD of n, GCD I n equal to the GCD of I n?
Because I said so.
Okay, that's it.
Because of complex number theory things, like, if you think about this, like, n and the largest common factor of I and n, well, the largest factor of I and n, the largest factor in common with n is just going to be the same as the largest common factor of I and n. It's very messy to pick apart, but it's sort of just like they're both getting at the same thing, the idea of greatest common factor that I and n have in common. Whatever the greatest common factor that I and n have in common is going to be the same thing that that factor itself, the largest common factor of that factor in n as well. That's a mouthful and a tongue twister to say. It's a good question. I did breeze over that because I was hoping I didn't have to. I was hoping no one would ask. All right, part 2. Do it yourself. Actually, part 2 follows pretty quickly from part 1. Basically saying, mainly because if these are equal, if and only if the GCD of I and n is equal to the GCD of j and n, then essentially part 2 is saying, what part 2 is saying is that the order of a to the I and the order of a to the j are equal if and only if they generate the same group, and that's something you can show fairly quickly using our previous results about the relationship between a cyclic group and the order of any element in the cyclic group. All right, here it comes. Fundamental theorem time. Fundamental theorem of cyclic groups. So this is going to be like our fifth most important theorem of the semester. There are going to be ones that I argue are more important, such as the theorem that says the order of any element in a group has to divide the order of the group. That's going to be a little more important. There's also going to be the fundamental theorem of finitely generated abelian groups, or as I like to call it, FGAG, as its abbreviation. And there's also some stuff with rings that's more important. There's also fit, the fit theorem. But this is going to be the most important one we've seen so far. The fact that it's fundamental theorem tells you it's probably one that's going to be useful. So here's what it says. We're going to let G be a cyclic group generated by A. Then it will be the case, here's the biggest part right here, every subgroup of G is cyclic. So in other words, the subgroup, any subgroup of a cyclic group itself has to be cyclic. Part 2 says that if the order of G is equal to n, then the order of any subgroup of G is a divisor of n. And the order of any subgroup of G must divide n. And third, this is kind of the coolest one to me, for every positive divisor k of n, the group G generated by A has exactly a single subgroup of that order. We have exactly one subgroup of order K, and I claim we can say exactly what that subgroup is. It's going to be the subgroup generated by A to the n divided by K. So basically, what this theorem tells us is it tells us the subgroup structure of every single cyclic group of finite order. It tells you can tell exactly what the subgroups are going to be just by looking at divisors of the order of the group at large. So let's look at an example where, before we actually prove this theorem, I think it's helpful to look at an example so we can get an illustration of what is this theorem actually telling us. And then we can start going through and actually proving it. Let's say our group is going to be Z mod 28Z. Z mod 28. So group of integers from 0 up to my favorite integer, 27, under addition mod 28. What would be a generator of Z mod 28Z? Peter?
1 through 27.
It's not going to be everything, because it has to be only things that are relatively prime to 28. The order of the group are going to be generators. So what would be an example of some integer that's relatively prime to 20?
27.
27. Dang it. I was hoping you'd say 1, because while 27 does work, for the only time in this course I don't want to use 27 as our example, because it makes it much more complicated. I'm going to go with 1, but this does work with 27 as well. Or 3 or 5 or 11 or anything else that's relatively prime to 28. So, first of all, if we want to find all the subgroups of Z mod 28, it's going to be helpful to find factors of 28. Anybody give me a factor of 28? Some number that for which 28 is a multiple. Rowan?
2.
2.
7.
7.
4.
4.
14.
14.
28.
28. 1. 1, 2, 3, 4, 5, 6, 1, 2, 3. Yeah, that's all. So, according to this theorem, I can tell you exactly what the subgroups of Z mod 28 are. Now we're going to talk about exactly, because according to this theorem, if these are all the factors of 28, 2, 7, 4, 14, 28, and 1, Z mod 28Z is going to have exactly one subgroup of each of these orders. For order 2, the subgroup of order 2 is just going to be, if our A here is 1, then our subgroup of order 2 is going to be A to the power of 28 over 2, which is in turn just going to be 1 to the 14th, which will be 14. And if we write that out as a group, it's going to be 14 and 0. Boom. According to the fundamental theorem, that's our only subgroup of order 2. And yes, when I say 1 to the 14th, I really mean 1 star, 1 plus 1 plus 1, 14 times. This is not the actual exponential function, but just the notation that we've been using. And so, if we're using our generator as 1, then all that we have to do to find our unique subgroup of order 2 is to basically take 1 to the power of 28 divided by 2. And that gave it to us. Similarly, if we want to find our subgroup of order 7, we'll take A to the power of 28 over 7, which is going to be 1 to the 4th, or 4. And that'll be, what? 4, 8, 12, 16, 20, 24, and 0. What's going to be a generator for our subgroup of order 4? Our subgroup of order 2 is generated by 14. Our subgroup of order 7 was generated by 4. It's going to generate our group of order 4. Peter? 28 divided by 4, which is 7. And so that'll give us a subgroup of 7, 14, 21, and 0. Subgroup of order 14, going to be generated by 1 to the power of 28 over 14, which is 2, which will give us 2, 4, 6, 22, 24, 26, 0. Subgroup of order 14 will give us all the even integers in Z mod 28. What's going to be our generator of a subgroup of order 28?
One.
Yeah, 1 to the power of 28 over 28, which is just 1, and that's going to generate the whole group. So this is our improper subgroup, the subgroup that's that's made up of the entire group. And finally, if we were to take 1 to the 28 over 1, what's that going to give us as our generator for our subgroup of order 1? Make I heart YouTube. Yes, thank you. This is going to be the identity. This is going to give us 28, which mod 28 is going to be 0. That's That's all the subgroups of Z mod 28 right there, according to this theorem. Is that the only subgroups are going to be ones that, of course, ones are going to be the unique subgroup whose size is equal to each individual factor of 28. And the fact that the group G has exactly one subgroup of each order is what tells us we don't need to look for other subgroups corresponding to each factor. Each factor is going to correspond to its own unique subgroup. Nick, do you have a question?
Well, I was just going to ask, are we able to say anything specific about the numbers that are not factors of 28? Like, we know that 27 corresponds to 1. Or is there some nice correspondence between generators that are not factors of 28? Or does it just depend on the group?
Yeah, well, technically we could say, but Dr. Gerstel, what about the subgroup generated by 27? It's just going to overlap with one of these. So basically, we do have a nice theorem that tells us something about when do two different elements in this group generate the same subgroup. Okay, that's precisely when. When they have the same GCD with 28. So since 1 and 27 both have the same GCD with 28, namely 1, they're going to generate the same group. Since 4 and what else? 4 and 8 have the same GCD with 28, namely 4. That's going to tell us the group generated by 8 will be the same as the subgroup generated by 4. So there's certainly going to be some overlap when you do this. You could say, but what about all the subgroups generated by all the other elements? But it's just going to be equal to one of these unique options that we've already seen. So to determine which one it is, just take your GCD with the order of the overall group, and whatever number that gets spit out, that's going to give you your equivalent subgroup. Good question, though. That's why it's helpful to have these sorts of theorems still, in order to kind of help us determine when are these certain types of things going to overlap with each other. Any other questions or comments? Okay, I guess let's start proving it. Does anyone want to take a guess as to which of these is the hardest to prove?
The third one.
Third one? Third one certainly looks the most complicated. First one to prove. Peter?
First one.
You're on a roll, Peter. I think it's number 1 as well. Number 3 is actually not so bad once you have number 1 and number 2. Number 1, it's your first one. The reason why number 1 is actually the hardest to prove is you have to come up with an argument that works for both finite and infinite groups. You can't give an argument that relies on something dividing the order of the group, because this result, at least for number 1, works if G is finite or infinite. It's for every cyclic group. Any subgroup of a cyclic group has to be cyclic, even in the infinite case. So let's see. You want to see what's ahead of you? Here's my proof for part 1. Not too bad, but it's going to take us a while. All right, here we go. So part 1, here's our proof. I already wrote proof. We're going to let G be a cyclic group generated by some element A, and we're going to suppose that H is a subgroup of G. So we're just going to take an arbitrary subgroup of our cyclic group G. Notice we're not making any claims on what the order of this group is. This could be like the integers. A could be like 1 in the group of all integers, and we would be having an infinite group. So our goal is going to be prove that H is cyclic. 2 cases. I'll do the hard case. Hard case is where H is the identity element. Then H is going to be generated by the identity element, and it's going to be cyclic. So in the case that H only has the identity element, clearly H is cyclic because it's just generated by its only element. Any of luck. Case 2 is going to be the fun one, which is H is not equal to the identity element. Well, why did I need to split this up into cases? Because the main bulk of this proof is going to rely on H having some non-identity element in it. Then I claim H contains at least one element of the form a to the t, where t is not equal to 0. So basically, we're going to have some non-zero power of a and h, assuming we're in the case where h is not literally just the identity element. Log t is greater than 0, since if not, a to the t inverse has to be contained in h. So we could replace a to the t with a to the t inverse equals a to the negative t. Has anybody ever seen this phrase before? WLOG. Right? What does it mean?
Without loss of generality.
It means without loss of generality. Basically saying, yes, technically, having some a to the t with t non-zero, we could have t being positive, or t could be negative, in theory. But I want to have a positive t, so if t is less than 0, just replace a to the t with a to the t inverse, because then that'll give you your positive value of a to a positive value. So we're just going to call a to the t is positive, because if it's the negative case, we can just swap it out with the inverse, and it doesn't matter which way. So without loss of generality is usually used to refer to these sorts of things where it's like, technically it could be one of two things, but in either way it kind of comes out to the same things, so just call it this one other. Just call it this one thing. Is what without loss of generality. Basically, we're just saying H has to have some positive power of A in it. By the way, if A to the T is in H, how do we know A to the negative T is in H? What is true about H that tells us if A to the T is in H, then the inverse of that thing is in H? Megan? Yeah, H is a subgroup, or it's a group, meaning the inverse of anything in H also has to be in H. So I didn't write it down, but we're implicitly using that property of groups. So we know we have some positive power A to the T. So now we know H has at least one positive power of T, A to the T. Or we know H has at least one A to the T where T is positive. Now, I'm going to let M be the smallest positive integer such that A to the M is an element in H. So in other words, I claim that, we know that there's at least one of these positive powers T, where A to the T is in H. We show that there's at least one of these things. If there's at least one of these positive powers, we know there has to be a smallest one. So we're just going to let M be that smallest power. We needed there to be at least one because technically I could otherwise say it's the smallest of a number of things that doesn't exist. What is the smallest, what is the size of the smallest, no, I'm not going to say that. That would get me in trouble. I'm not going to say it, no. Basically, we needed to show that there's at least one of these positive powers in order to be able to say, take the smallest one. My goal is going to be to show a to the m is going to be a generator for h. Because we can show that a to the m will generate h, then that will give us that h is cyclic, because it has a generator. So first of all, we know the group generated by a to the m has to be a subset of h by closure of h. So basically, if a to the m is in h, any power of a to the m is in h because h is closure and inverses and such. So we know everything in the group generated by a to the m has to be an element in h. So if we want to show these two things are equal, we're then also going to have to show that some arbitrary element in h is also going to have to be in the group generated by a to the m. That'll prove that's a subset of that, and thus the two sets are equal. So let's let B be an element of h. Our goal is going to be to show B has to be an element in this thing, group generated by a to the m. Since B is an element in G, which is generated by A, we know B is equal to, what did I call this? A to the k for some integer k. Because if B is in H is a subgroup of G, so B is an element in G. And if G is generated by the single element A, that means every element in G, including B, is going to be some power of A. And now, we're going to use the same theorem that we've used several times in kind of our previous theorems, by the division algorithm theorem. K is going to be equal to mq plus r for some q and r integers, with r being between 0 and m. So basically, k and m are two integers. I'm just using the division algorithm theorem to say, give me a q and an r that'll make all the things do the things. So in other words, k is equal to mq plus r. Our remainder term is going to be between 0 and m. Then, b, which by definition is a to the k, is going to be equal to a to the mq plus r, which is equal to a to the mq, a to the r. So b is equal to a to the m to the q times a to the r. Which in turn is going to tell us that a to the r has to be equal to a to the k, a to the negative mq. But what do we know? We know that since a to the k, which is b, is an element in h, and a to the negative mq, which is by definition a to the m to the negative q power, well, if a to the m is in h, that tells us a to the m to the negative q power has to be in h. Thus, a to the r, which is equal to the product of these two things in h, has to be, you guessed it, in h. So a to the r is going to be an element in h. We know that r has to be between 0 and m. But a to the m is the smallest positive, but m is the smallest positive integer with a to the m is in h. What does that tell us about r? If a to the r is in h, m is the smallest positive integer with a to the m in h, and r has to be strictly less than m. can we say has to be true about A to the R? Right?
It's, yeah, it's the identity because R has to be 0.
Yeah, R has to be 0, which means A to the 0 is the identity, which means A to the K, i.e. B, is really A to the MQ, which means that B is a power of A to the M, which means that B is going to be contained in A, or is going to be contained in this thing, which tells us that every element in H is going to be contained within this thing, which is going to tell us that H is equal to this thing, which is going to tell us that H is cyclic.
Too fast.
Because we're out of time. I'll write that all down on Monday. Sorry, ran out of time.